Hello everybody, welcome to tutorial problems in electrical circuit analysis. In this video we are going to see few theorems. The remaining part theorems we will see in the next videos. So the theorems what we are going to see I just listed on the next slide. So these are the different theorems: Thevenin, Norton theorem, superposition theorem, maximum power transfer theorem, Telegans theorem, compensation theorem, substitution theorem, reciprocity theorem, Millman's theorem and Miller's theorem. So, we will see theorems one by one. First, we will see the statement of the each theorem, then we will go to the problem in each theorem. First, we will see the Thevenin theorem. In any two terminal linear bilateral network can be replaced by an equivalent circuit consisting of a Thevenin voltage source with a Thevenin equivalent series resistance as shown in figure. So, here you can see the original circuit consists of n number of sources and n number of resistance or any passive element. So, it can be replaced with the single voltage source called Thevenin voltage and a single resistance as a Thevenin resistance. So, this we will see in detail in the problem session. So, we will see the problem in Thevenin. First problem, find the Thevenin equivalent for the following circuit. So, the circuit consists of two loops. Since for simplicity, for easy understanding, I just take only one source circuit, but with the help of this one the students can solve any type of circuit. Here the first circuit is given. So, once the circuit is given, so always remove the load resistance, then redraw the circuit. On the right hand side, I remove the load resistance, that is RL I removed, and I redraw the circuit. You can see here we have 15 ohm, 2 ohms, 2 ohms and 4 ohms. So, AB is the open terminal, that is called load resistance. Then once I draw the circuit, the next thing I am finding out the Thevenin resistance. So, as per the statement of problem, we have to find out two things. One is Thevenin resistance, other one is the Thevenin voltage. First I am finding out the Thevenin resistance. So, in order to find out the Thevenin resistance, we have to follow the two rules. One is, if you have a voltage source, we have to short circuit it, and if you have a current source, open circuit it. Since in this circuit we have only one voltage source, I am just shorting the terminal and redrawing the circuit once again. So, after removing the source, and then I got the circuit like this. So, now find out the resistance across AB. So, you can know that 2 and 4 are parallel with each other, that is in series with the 2 ohms. So, after simplifying it, I got the resistance 3.33 ohms. There is 2 and 4 are parallel, 2 into 4 divided by 2 plus 4 is 1.33, and it is series with the 2 ohms, that is 3.33 ohms. So, once you got the Thevenin resistance, then you go to the Thevenin voltage. Thevenin voltage is otherwise called as open circuit voltage. The voltage across the load is called as a open circuit voltage or Thevenin voltage. So, I once again got the circuit which I redrawn in the first step. I take that circuit and find out the voltage across VAB, that is called as VTH. So, since we have only one loop, if you look at the circuit, we have only one loop. The second loop is open. So, no current will be flow in the open loop. We have only one loop. So, open loop, no current flow. So, we are taking that first loop, the closed loop alone we are taking. So, applying the KVL. So, it is 15 equal to 2I plus 4I. So, after simplifying and getting I equal to 2.5 amps. So, this current is the current in the loop, but we want the voltage across VAB. Since the current in the 2 ohms is 0, so we are not considering that resistance. So, we are taking only with the voltage across 4 ohms. So, what are the voltage across 4 ohms? That voltage will be getting across a VAB, because parallel one point, another point, the resistance 2 ohms is considered as a 0. So, whatever the voltage you are getting 4 ohms, that is the voltage across the VAB. So, multiply the 2.5 into 4, so that will be 10 volts. So, we will be getting the 10 volts here, I drawn it. So, this is the equivalent circuit of the Thevenin. So, we have a Thevenin voltage 10 volt and the Thevenin resistance 3.3. So, finally, we bring the load resistance across the point AB. So, suppose in question they asked find out the current in the load resistance, apply KVL once again, find out the current I. So, this way we can find out the Thevenin theorem. So, the same theorem we are applying for the AC. Once again I am taking a simple problem for understanding the AC circuit. The rules is same rule. Only the calculation is different between the AC and DC problems. So, we will go to the question. Find the current through the branch AB of the network shown in figure using Thevenin theorem. So, we have only one voltage source, but we have many passive elements R, L, we have like this. So, what I told, first we have to remove the load. Here load is AB is 5 ohms, that I am removing it and I redraw the circuit. Once I redraw the circuit, next section I want to find out the ZTH. In case of DC it is RTH, in case of AC it is ZTH. So, I am finding out the resistance across AB. So, same rule is applied, voltage source short circuited, current source open source. So, I am finding out the resistance across AB. So, if you see 5 ohms is in parallel with 3 and J4 ohms. So, I simplified here. I am applying all the rules of rectangle to polar, polar to rectangle conversions and dividing it and subtracting it. All the things I done, and then finally I got 2.5 plus 1.2. So, students can check the answers with help of this calculation whether it's okay. Okay. So, you can check the answers step by step. So, I given all the steps clearly one by one. Next, the answer what we got it is in series with the J5 ohm. So, I made it, this thing is in series. Then and once again I do the rectangular to polar, polar to rectangle conversion, everything I done. Finally, I got 6.73 angle 68.20. So, now we got the thing. Next one is we have to find out VTH. So, once again as I mentioned in the previous problem, it is a single loop problem. So, only we can get the current in only one loop. So, once again apply KVL. So, as per the KVL I wrote the equation 10 angle 0 phi I plus 3 plus J4I. Find out the I. So, once again do all the conversions, rectangle to polar, polar to rectangle, division, subtraction, do all things, and then finally get the answer in the form of polar format. So, I equal to 1.11 angle minus 26.57 amps. So, that is the current which is flowing in the loop. So, multiply the current with the 3 plus J4. So, that is the voltage, open circuit voltage of this given circuit. So, it is 5.55 angle 26.57 voltage. So, it is the same rule applied whatever we done it in DC, but only the calculation, the rectangular and polar calculations will be different. Other things is looks the same. So, once the circuit is over, we have to redraw the equivalent circuit of Thevenin. You can see that 5.55 angle 26.57 is VTH and 2.50 plus J26 is the RTH, ZTH. So, now bring the load, whichever load we removed from the first step, bring it here and connect that thing to the Thevenin circuit, not to the original circuit, the connect to the Thevenin circuit. So, since in this question they ask the current flowing through the 5 ohms. So, once again apply KVL, write down the equation, then simplify it, find out the I. So, the I is 0.56 angle minus 13.24. So, all the rules are looks similar, only the calculation, once again I repeat, only the calculation is different between the AC and DC. So, this rule can be applied for DC also, and whatever the rule we follow in DC, the same thing is applied in AC also. So, only the calculation, conversion calculation only the different. Next one is Norton theorem. In any two-terminal linear bilateral network consisting of a number of voltage source and resistors can be replaced by a simple equivalent circuit consisting of a current source IN in parallel with a resistance. So, this is the original circuit. We have n number of source can be there, n number of resistance will be there with a load resistance. It can be replaced with a current source IN and then equivalent resistance RN, then load resistance. So, the difference between Thevenin and Norton is, so Thevenin deals with the voltage, Norton deals with the current, that is short circuit current, there it is open circuited voltage. So, we will go to the problem to understand the Norton theorem. Determine the Norton equivalent circuit for the circuit shown in figure. So, once again one small information. So, whatever the equivalent resistance we are finding out in Norton and Thevenin looks like both are same way, same procedure, everything is the same, only the notation is different. In Thevenin we have to put RTH, in Norton we have to put RN, only this is two difference, other things are same. So, the circuit is given here, you can look out the circuit. So, what are the rules I said? The same thing rule applied for to find out the RN also, remove the load resistance and apply the rule. What rule? Voltage source short circuited, current source open circuited. Apply this rule and read other circuit, find out the RN across AB. So, I applied the rule. So, 2 is parallel with the 3, so that is 1.2, that is in series with the 4 ohms, that is 5.2 ohms. Next is In Norton, we have to find out the short circuit current across the load. So, whatever the load we removed, that point we have to short it out. So, once you short out, the circuit will look like this one. So, we have a 2 loop circuit. So, the students can apply either mesh analysis in the form of KVL or inspection method, or if they convert comfortable with nodal analysis, they can apply the nodal analysis. So, I use a nodal analysis method to find out the current in a AB. So, you can see the nodal equation, it is only one node here, this is the one node here. So, V minus 25 divided by 2, V by 3 and V by 4, V by 4. So, solve this equation, then I get V equal to 11.57. So, that is the voltage at the point node V1 here, this voltage. So, now we have as a current and the AB point. So, the current in V3 ohm and V4 ohms look same, right. So, it is 11.57 only. So, divided by 4. So, we will be getting the current in that particular branch, this branch. So, it will be 2.89 amps. So, this is called as the short circuited current, that is called Norton current. So, Norton is represented as a short circuited current, Thevenin is represented as open circuit voltage. So, now we go to the equivalent circuit. So, now this is the equivalent circuit of the Norton theorem. So, 2.89 is the current what we applied as short circuited current, and 5.2 ohms is the, we got the Rn equivalent resistance, then 5 ohms is the load resistance. So, put all the values as in the original circuit, that is Norton circuit, then apply a current division rule. So, now we want the current in the load IL, that is 5 ohms. So, apply current division rule. What is current division rule? Opposite resistance divided by sum of the resistance into total current. So, here opposite resistance for 5 ohms is 5.2 divided by sum of the resistance 5 plus 5.2 into total current 2.8. So, we got 1.5. So, next we will go to maximum power transfer theorem. We will see the statement first. According to the maximum power transfer theorem, the variable load resistance will receive its maximum power from the DC voltage source only when the load resistance is equal to the source resistance. That is, whenever the load resistance is equal to source resistance, so we will get the maximum power. So, that is the statement is representing. So, to find out the formula, PL equal to VTH square by 4 RTH. So, this problem is similar to the Thevenin theorem, only the last step will be differ from Thevenin theorem. We will see one problem in this. So, fourth problem, obtain the Norton models and find the maximum power that can be transferred to the 100 ohm load resistance in the circuit shown below. Here in this problem they asked two things, one is Norton model and another one is maximum power transfer. So, for Norton model alone we can use that 100 ohms. For maximum power transfer theorem, the load will be whatever the load we obtained as a RTH, R Thevenin resistance is called as a load resistance. So, the RL we could not able to use for maximum power calculation. So, for maximum power calculation we have to use only the RTH resistance. So, Norton model alone we can use the 100 ohms. So, we will see I will do this problem. So, as per the statement what I told earlier, so remove the load resistance. So, in both the cases, whatever the things Norton model or maximum power transfer theorem or Thevenin theorem, first remove the load resistance and read out the circuit. So, I remove the load as mentioned in the question, then I read out the circuit, this is the circuit I obtained. Then first step to find out the Rn or RTH. If it is a Norton, it is Rn, if it is a Thevenin, RTH. For maximum transfer theorem also we can mention it as RTH. Okay. Then as the rules will be applied, voltage source short circuited, then current source open circuited, apply the rule, then I got this circuit. Then if you looked out 220 ohm is parallel with 470 and similarly 330 is parallel with the 200. So, these two are parallel and these two are parallel. Once these two are parallel, then the result will be become series. So, you can see the thing calculations you can see. So, 220 parallel 470 I got 149.85. 330 parallel 200 I have got 124.52. So, these both are finally series. So, I got 274.37. So, once we got RTH we can go for VTH. So, first we will be doing the maximum power transfer theorem. So, if you look out the, so RTH I already mentioned it is open circuit voltage, sorry VTH is I mentioned already is open circuit voltage. So, read out the circuit once again, the initial circuit what we obtained, and then find out the VAB or VTH or VOC. So, if you look at the circuit, it is looks at 2 loop circuit because the center part is open, we do not have a closed loop. So, we should not take it as a loop. So, only we have first loop and third loop. So, we have 2 loop totally. So, apply KVL for this 2 loop. I wrote the equation 10 equal to 220 I1 plus 330 I1. So, I got 0.014 amps for the first loop. Similarly, First, once I got the current, I am finding out the voltage across 470. So 470 ohms equal to 0.0104 into 470, I got 6.58. Similarly, the other loop, second loop, 5 equal to 200 I1 plus 330 I1. So I got 0.09. So I got the current, then multiply that 0.009 into 330, I got 2.97. So this is the voltage got it across the 470 and the 330. So please subtract the higher potential minus lower potential. So that is the voltage across VAB, 3.61 volts. This is the voltage across VAB. So now we go to the maximum power transfer theorem. So once again, as I mentioned earlier, so it is similar, looks like a Thevenin theorem. So read out the Thevenin equivalent circuit and put the load resistance. But here the load is RL is nothing but RTH. So we can put 274.37 as the RL. So 3.61 is the Thevenin voltage and 274.37 is the Thevenin resistance and 274.37 is the load resistance. So read out the circuit, then go to the formula of max power transfer PT equal to VTH square by 4RT. Substitute all the values, then I got 11.87 milliwatts. So this is the way how can I apply power in the max. The same circuit I am starting with the Norton theorem. So Norton theorem, as I mentioned, it's a short circuited current. So the what are the load I removed the load and short circuit this point. You can see this point. This is a short circuited point. So short circuit, once you short circuit, you can see the circuit. It have a 3 loop circuit. We have a 3 loop circuit. So either you can apply inspection method or KVL method. Here I use inspection method since because I need only the current in the second loop. So that's why I used directly inspection method to find out the I2. So no need to write down the entire equation to solve the problem. So the students who whichever method is convenient, they can solve it, but the ultimate aim is you have to find out the short circuit current. So I obtained this matrix. This is discussed how you can put the matrix in the previous videos. So you can refer the previous video to know how to construct this matrix. So for quick reference, I just tell it in briefly. So the 690 is the first to sum of the element in the first loop. 470 is the common between 1 and 2, and 0 is the common between 1 and 3. Similarly, second row is common between 2 and 1, and 800 is the sum of the element in the second loop, and 330 is the common between 2 and 3. Third row will be common between 3 and 1, and 330 is a common between 2 and 3, and 530 is the sum of the element in the second loop. So I1, I2, I3. So there are 3 loops. Then voltage will be 10 in the first loop, 0 in the second loop, and 5 volts into that. So find out the delta from this. So I got 100.4 mega ohms. Then find out the delta 2. Why I am finding delta 2? Because we need only the current in the short circuit path. Only the second loop I want. So once again replace the second column with the voltage source, and then find out the delta 2. I got minus 3.62 mega ohm. Then divide it. Finally I got minus 36.05 milliamps. So I2 equal to 3.62 milliamps. Sorry, I2 will be 36.05 milliamps. So this is the current, I got it in the second loop. So once again take that short circuit current as a Norton current, 36.05 into 10 power minus 3, and then 274.37 ohms and 100 ohms. Then use the current division rule. So opposite resistance by sum of the resistance into total current. So 36.05 milliamps multiply. So we got finally 26.75 milliamps is the current flowing through the load. So this way you can find out the current in the Norton. Next one is superposition theorem. You go to the statement. In any linear active bilateral network with multiple sources, the superposition theorem states that the response across any element is the total of response from each source taken into consideration independently, and the internal resistance of each source replaces the response from the other source. In networks with 2 or more connected sources, the superposition theorem is employed to solve the network. So it is in very brief. So if more than one source in a circuit, we can solve the problem with keeping only one source at a time, applying the rule, and that current, whatever the current or voltage which is flowing to the particular resistance, we will keep it as separately. Then separate circuits we can find it out with a single source, and finally we can sum up the things. That is the results of the superposition theorem. So this way we can find it out. We can go to the problem. Estimate the current through 5 ohm resistor using superposition theorem in the circuit shown in figure. This is a circuit given. You can refer the circuit. So here we have 3 sources. So we have to have 3 circuits. We will see the circuit one by one. So I am going to the first circuit. So applying the rule is same. Voltage source short circuited, current source open circuited. So I am keeping the 9 amps as the first source and eliminating the other 2 sources. So I am removing the 4 amps. So current open circuited, voltage source 32 volt short circuited. So I redraw the circuit. So after redrawing it, then if you look at the circuit, no need to confuse, we can easily apply the current division rule. So 2 and 4 are parallel with each other, that is 1.33 ohms, and 10 ohm is series with the 1.33 ohms. So we have to find out the current in 5 ohms resistance. So apply current division rule. So opposite resistance is 10 plus 1.33. So 11.33 divided by sum of the resistance 5 plus 11.33 into 9, that is 6.24 amps. So this is the current in the first circuit. So go to the second circuit. I am keeping the 4 amps only this time and eliminating the other 2 sources. That is, I am eliminating the 32 volt and 9 amps. So 9 amps is the current source. It is open circuited. 32 volt voltage source I am short circuiting it. Once again, it is very easy to apply the current division rule. 4 and 2 is once again parallel. That is 1.33. So it is in series with the 5 ohms, and that is the 2 resistance will be parallel with the unrooms. But we need the current in the 5 ohm resistance. Okay, so the current in 5 ohms and 1.3 ohms is same. Okay, so series current will be look same. So what I am doing, once again I am taking this branch as a single resistance, that is 1.33 plus 5 I am taking, it is 6.33. So opposite resistance is 10 ohms divided by sum of the resistance. So 10 divided by 10 plus 6.33. So you can have a question why I am choosing a 10, why I am choosing a 6.33 instead of 5. Because here this 5 ohm resistance and 1.33 are in series with each other. The current in 5 ohms and 1.3 are same because it is a series circuit. So that's the reason we have I am taking as a 6.33 in place of 5. So 10 divided by 6.33, 10 divided by 10 plus 6.33 into the total current 4 amps. So it will be 1.55. The next is only I am keeping the voltage source and eliminating the current source. So current source eliminated means open circuited. So apply the KVL equation. I am writing the 2 loops we have. The direction of the current is given in the question itself. So 32 equal to 4I1 plus 2I1 plus I2, that is the first loop. Second loop, 32 equal to 5I2 plus 10I2 plus 2I2 plus I1. So expand this equation, solve using the calculator, then I finally got I1 is 4.89 and I2 is 1.30 amps. So I2 is the current which is flowing in the 5 ohms also. So that is the same current, I2 equal to 5 ohms, 3 ohms. So this is the current in the third circuit. Now we got all these 3 current. So as per the superposition principle, the current in the first circuit, current in the second circuit, and current in the third circuit, we can add it. Since there are 3 sources, we have 3 circuits, or 6.24, 1.55, 1. So this is the current of the superposition. 9.09 amps is the current in the 5 ohm resistor. So that is the end of the tutorial. So we will see the remaining theorems and the AC problems also in later videos. Thank you for watching. Next video will solve the problems and theorem part. Thank you.